By the year 2050, the sea level along U.S. coastlines will rise by as much as 1. They're also predicting the levels will increase as much in the next 30 years.
Off the southeastern coast of the United States, marine researchers have made a discovery that is shaking the foundations of their understanding of the ocean floor. Near the Florida continental shelf, a series of massive oceanic sinkholes have suddenly appeared. Some large enough to swallow entire buildings, and others extending deep into the dark unknown. The initial discovery came during a routine mapping expedition conducted by a team of geologists and oceanographers who were surveying the seafloor topography for changes related to sediment displacement. What they found was far from routine. Sophisticated sonar equipment began registering vast gaping voids where previously there had been solid sediment-packed seabed. Before we start, smash the like and subscribe buttons for more updates. At first, researchers thought it might be an equipment malfunction. But after repeated passes over the same area and confirmation from multiple instruments on separate vessels, it became clear that something had dramatically altered the seafloor. These weren't minor depressions or slow-forming hollows. They were full-blown chasms, sudden cavernous sinkholes, some over 100 feet wide and plunging hundreds of feet down. The data sent shockwaves through the scientific community, especially given the region's previous reputation for geological stability. Unlike sinkholes on land, which are typically tied to groundwater erosion or the collapse of subterranean limestone, these oceanic anomalies appeared with no warning, no gradual erosion indicators, and no seismic activity to precede them. The floor simply gave way. Some of the most profound holes have an eerie symmetry, almost like pits drilled into the ocean bed by some colossal machine. Their shape is not ragged or chaotic, but disturbingly uniform in certain cases, which adds to the mystery and unease surrounding the discovery. The exact locations of these sinkholes have not been made public to avoid mass speculation or panic, but it is confirmed they lie within a zone previously studied for coral reef restoration and deep-sea mining assessments. That fact makes the sudden collapse even more puzzling, as years of environmental surveys had shown nothing to suggest instability. The sediment composition, water temperature, salinity, and tectonic readings were all within expected ranges. The presence of such massive voids challenges every baseline assumption about the ocean floor in this region. More disturbing than their size is their number. Initially thought to be a localized phenomenon, further exploration revealed that the sinkholes were not isolated, but part of a network stretching across several dozen nautical miles. They seem to align along a rough diagonal, suggesting a kind of subsurface pattern or force at play. One theory proposes the collapse of long-buried ancient riverbeds or caverns beneath the seabed, suddenly caving in after millennia of structural weakening. Another possibility, more alarming, is that these are signs of deep methane pocket collapses, similar to what has been documented in parts of Siberia, but never before at this scale in the ocean. The implications of this phenomenon are profound. The sudden appearance of large sinkholes could signal the destabilization of the continental shelf itself. If the shelf were to weaken over a broader area, it could result in underwater landslides of enormous proportions. Such landslides are not just geological curiosities, they can generate tsunamis. The infamous Storegga slide off the coast of Norway thousands of years ago created a massive tsunami that affected multiple coastal regions. If something similar occurred off the coast of Florida, the ramifications for the southeastern United States and even parts of the Caribbean could be catastrophic. These sinkholes also present serious concerns for marine ecosystems. The Florida shelf is home to a diverse range of sea life, including rare corals, endangered fish species, and vast fields of seagrass that serve as breeding grounds for numerous marine animals. The appearance of these sinkholes has disrupted local currents and caused a drop in benthic activity. Submersible footage shows the edges of these holes littered with disoriented or dead sea creatures, some pulled into the abyss by the strong downdrafts created as water rushes to fill the newly formed voids. Microbial communities that once thrived in sediment-rich layers have vanished in the areas immediately surrounding the collapses. The loss of marine life and alteration of habitats could ripple across the food chain. Fish that depend on specific temperature layers and current patterns may migrate or perish. Larger predators could be forced closer to shore in search of prey, altering fishing patterns and raising risks of human-animal conflicts. Coral bleaching, already an issue due to climate change, might accelerate in areas where sediment disruption increases water turbidity and blocks light. Infrastructure is another key area of concern. Offshore drilling operations, underwater cables, and even planned subsea tunnels are suddenly in question. The sea, vast and largely unmapped, has again reminded humanity of its capacity for surprise and for silent transformation on an epic scale. There is a psychological weight to this discovery too. As much as it is a scientific anomaly, it is also a symbol, a reminder of how much remains unknown beneath the waves. With so much focus placed on climate change, melting ice caps, and rising seas, the notion that the very floor beneath those seas might be shifting, collapsing, vanishing, adds a new layer of anxiety to our collective understanding of Earth's fragility. The next phase of investigation will involve deep penetration sonar and sub-bottom profiling to uncover what lies beneath the voids. Some hope it will provide answers, others fear it will raise more questions. Already, whispered comparisons are being drawn to the Bermuda Triangle, another marine mystery off Florida's coast. While the Florida sinkholes are grounded in science, the unexplained nature of their formation adds a layer of intrigue that defies easy categorization. One thing is certain: the seafloor is not the passive, unchanging canvas many once assumed. It is dynamic, volatile, and capable of transformations so vast and sudden they can rewrite entire geological maps. The Florida sinkholes have transformed a once quiet patch of ocean into a focal point for global marine research, where every new sonar pass, every core sample, and every dive might reveal the next clue, or the next collapse. As this mystery continues to unfold, the eyes of the scientific world remain fixed on the ocean's depths. What was once a routine expedition has become a race to understand an anomaly that could redefine our relationship with the sea itself. The magnitude of the Florida Oceanic Sinkholes cannot be overstated, not simply for their physical size, but for the new frontiers they are opening in oceanographic science. With every new day of exploration, the picture grows stranger and more complex. These sinkholes are not just holes in the seabed. They appear to be vast voids, revealing a stratigraphy unlike anything typically found at that depth. Marine researchers deploying high-resolution 3D sonar imaging have now detected vertical shaft-like features within several of the sinkholes. These shafts, many still unexplored, are aligned in layered corridors and pockets, not the chaotic, debris-filled chambers one might expect from a sudden geological collapse. Initial attempts to model their structure suggest some are more like vertical tunnels than cones or craters, descending hundreds of meters in straight lines with smooth inner walls, indicating erosion, or a process unknown to modern marine geology. It's not merely sediment that has disappeared, but perhaps deeper materials as well. One hypothesis now under review posits that deep-seated liquefaction may have occurred, an event where the seafloor substrate, under high pressure, abruptly changes from solid to fluid state due to stress shifts, causing entire columns of sediment to implode into the void. The uniformity and structure of some shafts are leading a handful of researchers to speculate whether gas expulsions, particularly from supercompressed pockets of methane hydrate, may be the underlying cause. Methane hydrates are crystalline substances found in deep marine sediments under high pressure and low temperature, where methane gas is trapped inside water ice structures. A subtle increase in water temperature or a decrease in pressure can destabilize them catastrophically. If vast pockets of hydrate dissociated simultaneously, the result could be a sudden vacuum collapse, explaining the sharp geometry and absence of gradual displacement indicators. But the idea of multiple simultaneous dissociation events introduces deeper concerns. For such an occurrence to happen across such a wide area, there would likely need to be a broader underlying process at play, perhaps related to long-term warming of the water column or destabilization of the thermal boundary layers near the seafloor. If ocean temperature has increased even slightly over the past few years in that region, it could trigger a chain reaction of hydrate collapse, not just in Florida, but potentially in hydrate-rich areas around the globe. This line of thinking raises alarm within climate science as well. Methane is a greenhouse gas significantly more potent than carbon dioxide in the short term. If hydrate fields are indeed beginning to destabilize at large scale beneath the ocean floor, a feedback loop could be initiated, where released methane warms the ocean further, triggering additional releases in other areas. Such a scenario has long been theorized in worst-case climate models, sometimes referred to as the Clathrate gun hypothesis, a tipping point event capable of rapid planetary warming. The Florida sinkholes in this context may represent the first visible warning shot. Another line of research focuses not on what has vanished. The Gulf Stream, a vital ocean current that plays a significant role in global climate regulation, flows near this region. Although current models suggest it's unlikely to be immediately affected, the potential for long-term disruption exists if sinkhole formation becomes more widespread, or if it begins to interfere with subsurface current channels that influence water temperature and salinity distribution. These shifts could alter hurricane patterns, intensify storms, or destabilize seasonal weather systems across the Atlantic. Adding another layer of concern is the fact that this entire event seems to have emerged without human detection until now. That raises troubling questions about how much we really know about the ocean floor. The technology exists to map Mars with greater detail than large parts of Earth's seabed. That fact alone makes the emergence of these sinkholes a wake-up call. If such massive and consequential geological events can take place mere miles from one of the most studied coastlines in the world without any advance warning, what else lies undetected in the abyssal dark? There is also the theoretical possibility that these sinkholes are not purely geological in origin. While not widely discussed in academic circles yet, a minority of researchers have raised questions about whether deep oceanic processes, such as sub-seafloor magma movement or supercritical fluid expansion, could be playing a role. The idea is not unprecedented. Hydrothermal vents and underwater volcanic eruptions have long been known to reshape seafloor topography. However, the geometry and abrupt nature of the Florida sinkholes differ significantly from volcanic or magmatic features, making these theories speculative at best for now. Yet speculation is hard to avoid when the normal rules of marine geology appear to be bent or broken. One unsettling observation from the dive footage shows that the sediment around the rims of the sinkholes is not just loose, but appears to be actively crumbling, as if the process is still underway. Small sediment slides and micro-collapses have been recorded in real time. In some cases, entire sections of the surrounding floor seem to sag slowly downward before snapping off and plunging into the depths. That kind of dynamic instability is rare and usually associated with earthquake zones, of which Florida is not one. What this means is that the sinkhole phenomenon may not be over. More openings could form at any time, and existing holes could widen or deepen without notice. The Florida shelf is now considered a zone of high geologic interest and potential hazard. Some expeditions have been paused out of safety concerns, especially those involving remotely operated vehicles or manned submersibles. The risk of equipment loss, or worse, human life, has become uncomfortably real. Oceanographic institutes across the world are now redirecting resources to better understand what's happening off the coast of Florida. Satellite radar altimetry is being employed to detect minute changes in ocean surface levels that might indicate further seafloor shifts. Deep-sea drones are being sent to map the full extent of the sinkholes and gather data on temperature, chemical composition, and sub-bottom layers. International collaboration is increasing, not just because of scientific curiosity, but out of a shared understanding that the oceans are interconnected systems. What happens near Florida may have consequences far beyond it. From a technical perspective, the event challenges foundational principles of sediment layering and compaction. Sediment cores pulled near the sinkholes show strange anomalies. Some layers are missing entirely, and others are more compressed than expected. In some cases, foreign materials like granular silica and rare mineral fragments have been found, hinting at older, deeper strata suddenly exposed. The age dating of these materials suggests some have not seen the light of day or touch of ocean water for millions of years. This opens the door to another, even more dramatic possibility that these sinkholes are exposing hidden geological features or ancient fault systems that have lain dormant under layers of stable seabed. If these systems are awakening now, the question becomes why, and what chain reaction might they trigger next? Is this part of a long-term natural cycle we've simply never observed before? Or is it a response to external pressures, such as climate-induced changes in sea level and water temperature? Even seasoned marine geologists admit that this event is unlike anything they've studied. It's not just the scale, but the suddenness, the silence of it all. No warning tremors, no detectable pressure buildup. Just absence. Land that once was, gone in an instant. For a discipline built on gradualism and slow change, the Florida sinkholes present a deeply unsettling contradiction, but on what might now be accessible. These sinkholes offer a direct window into previously unreachable layers of Earth's crust. Already, remotely operated vehicles, ROVs, have begun collecting samples from exposed formations that haven't been seen since ancient geological epochs. Some sedimentary bands suggest deposits dating back to the late Pliocene or earlier, giving scientists an unprecedented opportunity to study preserved materials untouched by ocean currents for millions of years. Among the early findings are microbial mats unlike any found in surrounding waters. These microbial colonies, clinging to the vertical walls within the sinkholes, exhibit unique chemical signatures, including the ability to metabolize sulfur and heavy metals under high pressure with efficiency never before recorded. Such findings open entirely new fields of biological and biochemical inquiry. Could these life forms represent ancient lineages, evolved in isolation deep within the Earth, now exposed by the collapse? Or are they extremophiles that migrated into the newly formed voids, adapting rapidly to an alien environment? More extraordinary are reports of faint bioluminescent emissions recorded in some of the deeper sinkholes. These lights, seen only at depths over 500 meters, pulse in rhythmic patterns unrelated to known marine bioluminescence. While this might be a natural optical illusion or related to chemical reactions in disturbed sediments, the possibility that undiscovered marine species might be involved has galvanized the attention of deep-sea biologists worldwide. The discovery of new life, particularly in the abyssal regions of Earth's oceans, is not rare. But the convergence of seismic, chemical, and biological anomalies in one location is extremely unusual. The engineering and logistical challenges involved in exploring these new depths are considerable. Even the most advanced ROVs struggle with the vertical descent and unstable edges of these formations. Sediment slides remain a constant threat, and the narrow shafts can become bottlenecks for tethered vehicles. In response, a new generation of untethered, AI-guided submersibles is being fast-tracked for deployment. These autonomous underwater explorers are smaller, more agile, and capable of real-time decision-making, allowing them to navigate spaces previously off-limits to human-designed missions. Some models are being outfitted with retractable sampling arms and modular sensors, giving them the ability to collect samples from areas too risky for traditional equipment. Meanwhile, satellite monitoring systems have begun to detect subtle changes in the sea surface elevation above the sinkhole field, suggesting ongoing subsidence beneath the shelf. The seafloor might still be settling, or more voids may be forming just beneath the crust. Oceanographers are studying whether these changes could eventually influence tidal patterns or even the local gravitational field. Tiny, perhaps imperceptible to most, but measurable by sensitive instruments. This leads into an entirely different set of concerns: the potential for interference with human-made systems. Deep ocean cables used for internet and communications run through parts of the Atlantic near this region. A significant seabed collapse could not only sever connections, but also cause shifts in pressure zones that affect cable tension and buoyancy. A sudden cable snap in high-pressure zones could lead to loss of connectivity or cascading mechanical failures extending across international networks. At present, redundancy systems would prevent major communication blackouts, but localized outages and repair challenges are very real. Even more worrying is the implication for offshore infrastructure. Florida's coast supports a network of oil and gas exploration platforms, as well as desalination plants, coastal defense systems, and undersea pipelines. Though none are yet known to be directly affected, the specter of future collapses expanding inland raises the question of long-term viability. If the geological underpinnings of the shelf are less stable than assumed, then structural reinforcements or relocation may become necessary for critical infrastructure in the years to come. But the implications do not end with technology or biology. They extend into geopolitics. Territorial claims over marine zones are often based on geological surveys and the presumed continuity of continental shelves. If large sections of a shelf collapse or are proven unstable, nations may find themselves renegotiating maritime boundaries. For example, exclusive economic zones (EEZs) may be challenged if baseline markers shift due to seafloor collapse. This could provoke legal disputes between coastal nations, especially in regions already fraught with maritime tension. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on these Florida sinkholes? What do you expect next? We want to hear from you. Thank you for watching and see you next time.